So mute.
See.
Sir, I gave you unmuted only.
Now, is it working? Fine. Okay. So we were having this stream of elements, as I told you, right? We want to estimate a function of vector x in Rn, and we initially assume that we have all 0 vectors, and each iteration we have like some update of like EJ in a stream is update of the form that okay, let's go to the ijth coordinate and update with delta j, where ij is in 1 to n. Okay, okay, and and this delta z or delta, all these delta j are in real numbers. Okay, so this update is like you go to xij, and now what you have done is xij plus delta j. Okay, and this delta j could be positive or negative. Okay, so if you recall, we said that if at any point of time, so in Turnstein model we don't care whether like you are allowed to do arbitrary of these things, but these functions could be negative, like these entries could be negative, positive, anything, we don't. But we have the notion of strict turnstile, which just meant that at any point of time in execution, these xi's are always greater than or equal to 0. Okay. Though, for example, I could have increased by 5 and then I have decreased by -3. So that's perfectly fine. So delta j's could be negative, but the value of xi throughout the process will always remain positive. Okay. Okay. So actually what people like to do is like, so these are the kind of models we have been talking towards the end of our last 2 weeks back when we left. And so for now, let's just assume that you're given these things and you want to find an element which has highest frequency. You want, so imagine yourself that these numbers are coming from 1 to n, right? So here, not only these are indexes, okay? Assume that delta j looks at ith coordinate when I say hey, is think of this that okay, at 5th coordinate means the 5th element has come 1 times or 2 times. So when I say frequency, I want to compute max of xi's. I want to compute this max value of xi. Okay, so am I interested in that I going from 1 to n give me max of xi. Okay, even with very simple case when like assume that all deltas are positive, it is 1, even then finding, so think of this space like you have n positive numbers and you want to compute a number which occurs the most number of times. Okay, that doesn't mean that's a majority element. There's a difference between a majority element and a number which occurs most number of times, right? Majority element means that it occurs at least n over 2 times, right? But I'm not interested. It could be that everybody occurs twice or thrice, and among them I would like to get the one which occurs the maximum number of times. Okay, so even when you have a sequence of like even if not in this model and you are told that all the numbers are between 1 to n and they're just coming here some m numbers and you have to give me which number has occurred most number of times, it is not possible to do quickly. Okay, okay, do you know any algorithm, just forget about offline online, if I ask you to find the most frequent element, uh, and now I don't give you guarantee that these numbers are from 1 to n, okay, or even if I give you a guarantee but I do not allow you lot of space, how much time will it take? Do you get my point? Median, all of us know how to find in linear time, but I am not interested in finding median, but I am interested in finding number with the highest frequency. Any algorithm? Okay, but that's like n log n time, right? And can you sort in n log n time in the same space if I don't allow you extra space? Can you sort in n log n time? Do you get my question? I have an array of n numbers and I want to sort these numbers, but I don't want to use more than constant number of extra space. Can we do it in n log n time? Quick sort. Quick sort. I quick sort could be very bad. Heap sort. Okay, I make my question more difficult. You're not allowed to move the order of the elements. And use small space. You get my point? Numbers, arrays, there are numbers, right? You do any sorting algorithm, they move things around. I'm telling you that you cannot change the order and use logs, small space. Because look, ultimately, if we are moving here, just to get you a feeling of why these things are difficult, is that here things are coming, I cannot store all of them, and so it's like I can see them once, but there you can go and see them as many times as possible, but you're still not allowed to change the order of things. How much was the restore model algorithm and log n? Sorting, restore model, sorting, if they're integers. Bit hacking. Not just comparisons. Yeah. So, I mean, just to get you a hang of all these things, I mean, though they sound very difficult, those sound very easy problem, the moment you talk about space and space efficient algorithms, even for these basic objects, it becomes very difficult. Okay. So, we don't know any algorithm, actually you can prove a lower bound of omega n space if the maximum frequency element is very small compared to the number of items. Okay, so suppose m items are going to come and the maximum frequency is some constant, then you can get an omega n space lower bound. And why omega n space lower bound? Because I told you the numbers are from 1 to n. So you can always do it in one, like in n space, like n times some number of, like on n counters you can always do, right? You have 1 to n, and for each item, whenever it comes, I just increase its counter. No, but this is in a streaming model, right? Which automatically means that you are not allowed to move anything. You are just going to see in one go. Okay, so this is why people start people. Yes, so this is why. So like, it is only says omega n bits. I don't know whether one can prove omega n word sized lower bound. This I don't know. But it wouldn't matter anyway, because as I told you, right, it is when the number of items are like constant. So I don't need more than constant number of bits at any way to store here. So in that sense, it is tight. Right? So even when there is an upper bound of constant on number of like number of times and items will be coming, you can prove such a lower bound. Okay, so this is why people are interested in what is called, so this is the reason why people are interested in what is called heavy hitters in streaming setting, because finding an element of maximum frequency even in such restricted setting when the numbers are coming 1 to n and blah is hard. Okay, so what is an heavy hitter problems? So in heavy hitters problem, you are given for all items I, okay, you want to find for all items I, okay, such that for all items I, such that frequency of I is m over k, okay, then output I, okay, and k is some fixed quantity. Okay, and when k equal to 2, this is basically majority, right? And last time we gave an algorithm for majority, if you recall correctly. Okay, so this is one streaming algorithm which we gave for majority last time. So let me write it down. Okay, majority was very simple. S was null, and while stream is not empty, what are we planning to do? We said that look, so what does it tells you? That look, it is storing a counter of the current element which we propose as a majority element, right? And S stores the current proposal for the majority element. So what we'll do, if my EJ is equal to S, then what should I do? I should increment my counter to C plus 1, okay? Now, if Cj equal to 0, C equal to 0, not Cj, then what should I do? It means, oh, I have no proposal at this point of time. Then what do? I make C equal to 1 and I assign S as EJ, right? So I check whether whatever I am proposing is what this EJ is. If yes, then I do C plus 1. Else, if C is 0, it means that I have no proposal for anybody. Then let me make this as my new proposal for majority. And what else we did? Else, okay, I have some proposal for the majority, but what is my current element is not what the proposed element is. Then what I say? I decrease C by C minus 1, okay? And while output is C. So basically what happens, if you look at this algorithm, then so you make up proposals, right? Same type. Now next guy comes, what happens? It is definitely not this type. So what are you doing actually? So what do? You delete, right? That is like you are pairing this with some of other kind, right? So if you are looking for a majority element, right? Majority element. So think of majority element. This is how you write your majority element, and this is how other element, right? And it's like, okay, I have done a pairing. Now I delete these two objects even. So whatever my current object is still is a majority of the remaining guy. So you should think of this whole process as like I am pairing up two objects and deleting it, right? Again, when next element comes, it is same element, then I incremented. If it is not same element, then I again found a pair and deleted it. So every time, what am I doing? Every time I find a pair where both elements are distinct and I'm deleting it. So if you look at this chart, this is my majority element and like which occurs large number of time and this. So it's like I'm playing a game, okay? So I took two guys. So I can think of this algorithm as like the moment I find two elements of the distinct kind, I throw them out, okay? Then I ask myself this oracle, oh, are there two elements of distinct kind? Yes, then give me, I throw them out. I keep doing this. If at the end, any element will survive, then that will be a majority element. It's a candidate for the majority. Sorry. It's a candidate for the majority element. It may not be the majority element, but it is a candidate for the majority element, right? So this is exactly what this algorithm is telling you, right? That, hey, I don't know whether this is a majority element or not, but this is definitely a candidate for the majority element. So if there exists a majority element, then this S will be storing that. So in the next pass, you can go and check whether that is a majority or not by checking how many times this occurs in the string, right? So do you get my point, right? So think of this as like a pairing up of two distinct elements and throwing them out, throwing them out, right? And whatever is left behind at the end is your potential candidate for the majority element, and you can check whether that's a majority element or not in the next round by checking how many times it occurs. You look very confused, Pratibha. There is no technique. This is an algorithm. I'm just trying to give an analysis. So what I'm saying, think of this way, that, okay, I try to pair them. I try to pair my set of elements. Forget about streaming, non-streaming. I will tell you, A1, A2, suppose I have AM, some M elements. You cannot see them, okay? You just ask, give me a pair of distinct elements, okay? So if there exists some pair of distinct element, then I give you. So I give you AI, AJ. What was the property of AI and AJ? AI is not equal to AJ. Now I throw this out, okay? I ask, yes? Okay. So I ask again, do you have some such pair? It gives me another pair. It gives me another pair. So, and suddenly this oracle tells me that, look, I have no such pairs left. It means whatever is remaining here, it's same element. Because if there would have been two distinct elements, my object will return, right? Okay, fine. So now notice, so now suppose it says, so then I ask, what element remaining in you? It tells me X, okay? My claim is X is a candidate for being a majority. Okay, why? Because look, every time I said, look, think of this as a majority as like one bucket, majority as one bucket, and non-majority elements as another bucket. What am I doing? I could have removed two elements from non-majority. It could have happened, but in that case, this guy still is a majority, right? Because for I could have picked up one element from here and one else. These are the only two things which are possible. But in this case, I decreased one from here, I decreased one from here. So the relative size of this box is still larger than this.
What are you assuming? Can there be two elements which are both majority? Like
No, I said strictly greater than m by 2. Okay, I need strictly more than half. So if it is 2n,
you don't want the maximum frequency, you want the majority element.
yes,
You don't want the maximum frequency, you want the majority element.
if there exists a majority element, that has to be maximum frequency. Yes, no, I do not want. We don't even know how to do it. Okay, so this is all that I was trying to tell you. But look, it could be that this box is very big and there is only one element here for all that you care, or very small number of elements. So I'm succeeding because of these, right? And now what is left is like some 3-4 elements, right? But maybe that is the only element here. It's not that I have been fighting with these kind of objects here, right? So it could be that what is my possible potential answer for majority is not a majority. This is why I need a second pass to check that what I believe is my majority is indeed a majority. Okay? And look, if I did this in one pass for majority, it is very clear that I can do. So in 2 pass, how much space did it take? All I stored is some two counters, right? So some order log n or log m, whatever you want to say. Okay? And the second round will take log m because I have to count the frequency of this. Right? Okay. So this is all is well if I wanted to find a majority. But what can I do if I am interested in finding all elements which occur say m by 3 times or which occurs m by 4 times? Can I generalize this algorithm to handle this case, right? And the reason why I told you that if you think of this algorithm as that, like at some point of time, I'm making some pairs, throwing maybe not pair, but maybe something else, maybe so maybe it is m by 4, then I make 4 distinct guys and throw them out, because it's like, you get my point? So the question is, how do we generalize this algorithm, right? So telling you the logic behind this was just that we may be able to generalize this values of k. Okay. Okay. So this is an algorithm given by what is called, if you look at Mithra, Grice. Okay. So it takes as a parameter k, and it will output you. And as always, this algorithm will also have second round, like second step, to check whether these are really the correct one. Okay. So it could also, so if you just ran only one round, you could have false positive. Okay. So okay. So what is this algorithm? So you have an associated array. Okay. In the beginning, it is empty. So what will I try to do is that at any point of time, what was I doing here? I said, hey, I'm storing some number. If that number came, I incremented its counter. This is what I did. So now I'm not storing one element, I will store certain number of elements. If the new element come is one of the ones which I have stored, I will increment its counter. If it is not, and my number of non-zero elements or the size of my D is less than k, then I will put it inside and increment its counter. So now the final case is when there are k of them, but I am not present here. Then what I have found? I have found k elements which are distinct, myself k plus 1, and I throw myself. Do you get my point? So what I do, I already have k elements, and they all are by definition distinct k elements which I am storing at any point of time. I came, k plus 1th element came, I check, am I inside any of this? They say no. Then I cannot increment any counter. And I cannot initiate a counter for myself because it's already full. But then what is an extra information I am able to get is that, oh, then these k elements are distinct and include me, then I have found k plus 1 distinct elements. Let's throw them out. And how do I achieve this? I throw him out and decrement the counter of each of these guys by 1. Right? So that's the overall design of the algorithm. Okay? So what I do, so let's just make it while is not empty, what are we going to do? We are going to do is the following. Suppose Ej is the current item, and what I will do is that I check if Ej is in keys of T. And what I mean by this, so think of this like D, I have like D has been like its positions are indexed by E1, E2, this is what I mean by keys. So D of Ej, if you like, then it will tell you how many times Ej occurs. This is what I mean by Ej is in the keys of T. Okay, then what I do, DAG is equal to whatever it was plus 1, right? I incremented it counter by 1. Maybe this is the right way to write. Okay, so this is parallel to this. Now second is if C equal to 0, it means there was no proposal. So which is equivalent to saying else if number of keys is less than equal to is strictly less than k, then what should we do? Then you make DEJ 1. So you initiated this. Okay. Else now this case does not occur. So this key doesn't appear. Number of keys is when I have come here, it is now equal to k. So what should I be doing? For each L in keys of D, what will I do? I will just decrement the key by -1. Okay? Remove elements from D whose counter becomes, whose counter values are 0. Okay? This wouldn't arise here, but since here we are maintaining too many of things, so okay. Now this is end while. Now what I'm going to do is for each I in keys of D, for each I keys of D, set Fi hat equal to Di. Okay? For each I not in keys of D, I set Fi hat equal to 0. So think of this way that for every element I'm telling you some approximation to its frequency. Right? So if some elements occurs less than m by k, its frequency is set to 0 for some reason. Right? Any key which is not selected in this has been set to 0. Okay? So theorem what I will prove to you in a minute is the following. For each I in 1 to n, okay, Fi minus m by k plus 1 is greater than equal to Fi hat is greater than equal to this, which is less than equal to real frequency of I. Okay? So what is the corollary of this if I prove this theorem? What is the corollary of this statement? So I have said something, right? So basically at any point of time at the end of my stream, I look at my D and say, hey, for any element, what is its current frequency? If this element is there, then I put it with D of I. If it is not there, then I just put it 0. Okay? Okay. So let's see what happens. So this is true about any Fi hat. The relation between for any element I, if you look at frequency, real frequency, and the frequency hat given by this is something which is satisfied. We'll prove this in a minute. Okay? But suppose we have proved this, does it imply our algorithm? I claim that any item with Fi equal to greater than m by k belongs to D. Like it must be belonging to D here. At the end of the algorithm, this guy must belong to this. What?
Can't those items also belong which have frequency greater than m by k plus 1?
Which has frequency?
Greater than m by k plus 1.
I never said they can't. All I said that any item with this definitely belongs to. I'm not saying anything more than that. Yes, it can. I mean, if even for two people could belong to. All I'm saying that if your frequency is more than m by k, you definitely belong. I'm not saying that if it is not, you don't belong. What? What are you saying? So are you trying to tell me that the item which is very small will never belong to D? That's not true. It was not even true for majority. So I mean, it could belong to D. My proposal could be just wrong.
If some frequency is greater than m by k, take k consecutive elements, you can greater than m by k, then fi hat would be greater than m by k minus m by k plus 1, and that would be.
So what does this tells you? It tells me that fi hat is at least fi minus mk plus 1, right? Okay. So which item's frequency is non-zero? Like some items frequency is non-zero, right? And I'm telling you that fi hat is definitely at least this much. Okay. So what I know about fi, this m over k plus 1. Fi hat is at least this much for element whose frequency is at least m over k, right? Which is m by 1 minus k by 1 k plus 1. This is a non-zero quantity, right? So the only, so what does it mean? If for some element my fi hat is a non-zero quantity, then it must belong to D, because the only way fi hat is non-zero if it belongs to D. Right? So of course it all hinges on how we prove that. But once we prove that, the corollary of that lemma is very simple. Corollary is any item whose frequency is high must belong to D, because that's the only way fi hat could be non-zero. Okay, so it is as simple as that. Okay. Now, how are we going to prove the statement? Now, can you tell me why this inequality holds? Isn't that obvious? At least that inequality is obvious. Why? Because I mean, what are we doing? Like we find an element, we never increment for any element more than the number of times it appears, right? Because what I do, look at this algorithm, I check when any item comes, do you belong? Then I increment your counter. Otherwise, someone and decrease its counter, but it will never increase its counter. So this upper bound always holds. So what is non-trivial is this part. Okay. Okay. So another way of looking at this algorithm, which is slightly more cleaner way of looking at this algorithm, is that your algorithm maintains a counter Ci. Okay. This is a view. It is not that this is what algorithm is doing, but algorithm maintains a counter C. Okay. For so you have n counters. So think of this as an array. Okay. Ith, it's a counter for I. Okay. Now, initially everything has been initialized to 0. Looking at this algorithm, what is one invariant this counter maintains? At most k items are non-zero at any point of time. at most k items are non-zero at any point. Okay? And when new element comes, element Ej comes, what are we doing? If C of Ej is greater than 0, then what you do? You increment the counter. Right? That's the only time when you increment the counter. Okay? Else, if less than k counter, okay, less than k positive counters, what you do? You make C of Ej equal to 1. Okay? Otherwise, what you are doing? Else, decrement all the positive counter by 1. This is exactly what the algorithm is doing. Right? And what is algorithm outputting at the end? Output fi hat equal to ci. That's it. This is exactly what the algorithm is doing. So you are maintaining. So in the beginning you have all zeros counter. Invariant is that at most k counters are going to be non-zero at any point of time during iteration of this algorithm. And when a new element comes, if its counter is positive, I increment its counter. Right? If the total number of positive counters is less than k minus 1, then I increment his counter by 1, or I decrease all the counter by 1. So this is the third step. And at the end, what is remaining here is that fi hat which I have been talking about. Okay. Now how do we prove this? Okay, so now, yes?
Here is another way of
Okay.
So what you are going back to your pair, distinct pair analogy, what you are doing is you are creating blocks of k plus 1 distinct elements.
That is what the proof is.
So you are creating blocks of k plus 1 distinct elements. So the moment you got k plus 1 elements, think of it as you are taking one copy of each of them and keeping them aside. That's exactly the decrement counter idea is. Okay? Anything which has become 0, you keep it aside and it doesn't get participate in the next block. So the moment it becomes k plus 1, keep it aside, keep it aside. So finally, what survives is the residual guys with their frequencies. Okay. So now, what can be the frequency of any element, whatever the residual frequency, plus 1 in each block, because each block is all distinct elements. So that 1 in each block is m by k plus 1. So fi is at most fi hat, which is the residual frequency, plus m by k plus 1.
Yes. This is exactly what the proof will be doing. So what we will show that fi minus fi hat is less than equal to m by k plus 1. Okay. Now suppose we had L occurrences of decrement. What does that imply? Suppose we had L occurrences of decrement, that is like k counters being decreased. So basically at that point of time, you have picked up k plus 1 distinct element and thrown them out. So what does that imply? That implies that k plus 1 into L is less than equal to m, where m is total number of elements. That is definitely more than this. Okay? Which implies the number of time you will be doing decrement operation. This implies the number of time you are doing decrement operation is upper bounded by k plus 1. Okay? Now generally for these kind of questions, the one easy way to analyze something is the following. So you consider, so in the beginning, so I look at, this is how I wrote down this counter, and I want to understand how fi and fi hat behaves with each other. So consider alpha equal to fi minus fi hat. Like as items are processed, okay, as items are processed. Now what happens in the beginning, fi and fi hat is 0, nothing has been processed. So fi and fi hat are same, so this implies fi minus, this implies alpha equal to 0. Now question is, how big can alpha be, right? How big can alpha be? How big can alpha be? So we will upper bound this alpha by number of decrement operation, and the moment we are able to bound alpha by number of times we do decrement operation, we will be able to get what we wanted. Now if Ej is I and Cag right, if Ej is I and Cej is incremented, what happens? Look, suppose Ej is I and Ci is incremented, what happens then? At that point of time, look, frequency has changed by 1, but frequency hat also has changed by 1. Because what is frequency hat? Whatever is in my current C. So at that point of time, this quantity doesn't, like the alpha could be anything, but alpha after this process is not going to change, because Fi also has increased by 1, Fi hat also increased by 1. Okay. So and Ci is incremented and then alpha stays the same. Next what happens if Ej is equal to I and Ci is not incremented, okay, then what happens? Ci is not incremented, then we are in the last case. Then what happens is that alpha increases by 1. Why alpha increases by 1? Because why will alpha increase by 1 in this case? Because this will decrease by 1, because you are going to decrement k counters. So if you decrement k counters, this quantity will change. Okay, is not incremented and k counters are decremented. So in this case what happens? This is not incremented and k counters has been decremented. You charge it to L, right? Because what are we saying? That this quantity, like yes, alpha has increased, but I charge it to L. Charge it to L, the decrement operation. Last case is when if Ej is not equal to I, okay, and alpha increases by 1. Alpha increases by 1. What happens if Ej is not equal to Y and then in this case what we did? Wait. Alpha increases by 1 because what happens? If Ej is not equal to 1 and alpha, right? If Ej is not equal to 1 and alpha increases by 1, then it is because what happens is that Ci is incremented, okay, sorry, Ci is decremented, yes, Ci is decremented, then in this case we will again charge it to L. So what happened? Let's see, right? So now my EJ is coming. I check whether you are equal to I or not. So you are equal to I, and Ci is incremented. Then alpha stays the same. So in which cases this will happen? In both cases it will happen. Either this guy belongs to this, in that case Ci has increased, or if if it does not belong but the number of keys is less, at that point of time also this counter will increase. Okay. So if EJ is equal to I and Ci is incremented, then alpha remains the same. Okay. So that takes care of which cases? This case and this case. Okay. Now EJ is I and Ci is not incremented, right? This element has come but Ci has not been incremented. What happens then?
Because there are already key distinct elements.
Exactly. So because I came, but I am not increasing myself. But look, my frequency has changed, right? Because look, I'm not doing anything to the counter, but my frequency has changed, right? Fi hat is not changing because I'm not going and making any changes to my counter, right? But what that initiates? That initiates that K counter should be decreased, right? So you charge that to the decrement operation, right? So it is the case when this one happens. This case happens, right? That I am the element, but I don't increment my counter. I don't increment my counter because A, I do not belong to the keys, and B, number of keys are equal to K. So that is when this. Or what can happen? When an item has come, okay, and it is not equal to 1, then in that case alpha increases by 1 because Ci is again decremented. You get my point? Look, someone else comes and decreases me. Look, not only I can decrease it, but someone else comes, right, and he sees that there are K elements. At that time also my value will decrease. So Fi hat is decreased by 1, in which case this quantity will increase by 1. But again you can charge that step to one of the decrement operation which brought it to this. Okay. So in either case, what does it mean? So for every change in alpha, you are able to map it to either this alpha never changes, or if it changes positively, then you are able to map it to one of the decrement operation which be upper bounded by m by k plus 1. Okay. So what does this implies is this theorem. Okay. Okay. So let's see how much space does this algorithm take. So we have order k counters. Okay. So it is going to be take like log n plus log n. Because for the second pass to check whether these are the really m by k elements, I need to. Okay. So this is deterministic and it outputs all the heavy elements. But look at this algorithm, like I mean, you can implement this algorithm in linear time and output all the if I'm interested in not only majority but all the elements of frequency like which occurs m by 3 times or m by 4 times or m by 5 times, I can run this algorithm and output them and check because going by the second pass, and this will be a linear time algorithm. Okay. So we cannot improve this deterministic algorithm if we are looking for an additive error of roughly m over k plus 1. This is like an additive error of m over k plus 1, right? So we cannot, right? What I mean by this, like for the frequency, which ones are set to 0? If they occur less than equal to m by k plus 1, definitely very good chance they are set to 0. But anyway, it's so every frequency fi tilde which I will output to you is in the range between, this is the range because this is what I output you. right? So this is an additive approximation of m by k plus 1, right? So this algorithm gives you an additive error of m by k, that's it, right? But we cannot hope to achieve what you call, so if we want a less space algorithm and want an additive approximation, then we cannot do better than this, okay? So in that sense it is optimal, okay? So now we are going to look at randomized algorithm. So up until now, something which I assumed here is that I never assumed deletion. I said, okay, positive numbers are coming and this and that. So we will now we'll give an algorithm where elements can also be deleted, and still you can at the end you will know how much frequency is, right? This algorithm will not work even if I say now let's delete it. All the analysis will backfire, because maybe the group which you made to throw, now that group doesn't exist, that group doesn't contribute that element, right? So even though I told you at the end every guy occurs positively, right? Every guy, even if I told you occurs positively, like so, but decrease, increase, this algorithm cannot support this kind of thing. So we like to have some deletion operation, and so we will do what we will call sketch based approach. Okay, so now what I want to do, okay, any question here, because now we will change gears and do something very different. Like problem remains the same, it's just that we will do a very different algorithm. Okay. So now we will completely work in strict turnstile model. Okay, and we have like x1, x2, dot 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 xn, and what is our goal? Okay, so it's a strict turnstile model. So throughout the process, I will assume that xi is greater than or equal to 0. It never becomes negative. Okay, for all time. Okay. So and what we want is some sort of additive error to xi. Okay, I'm not assuming anymore that from where this element comes or nothing. I want what these values are. Okay. Right? And think of this way, that I want top k values here. Look, these xi's are greater than or equal to 0. So then there's a notion of top k values, or notion of which values occur most number of times, things like that. Okay. So again, so our question, I mean, just to make your life easier or harder, I don't know. If you don't want to think, just think of these are like 1 to n, like this is 1 to n, and I'll tell you whether, like when I say plus 1 means 2 has come once time, when I say minus 3 means, and I say I comma minus 3, it just means that for number I want you to reduce the number of times it occurs by minus 3. So it is storing your frequency, but I mean, this is what I'm interested in. I don't show you, but I tell you that now at ith place, please reduce by minus 3, right? And at the end, you have some numbers which are all greater than or equal to 0 by our assumption. And what I would like to output, all those numbers here or items here which appears more than m by k times. Okay, so think of this as a still frequency f1, fn, and I want to output all fi which is greater than or equal to, which is strictly more than m by k. Okay, but now I allow you to decrease its frequency. Okay, so the idea is for this algorithm is slightly different than what we have been doing. So why all these algorithms works only for this, you will understand now, that what I would like to do is that, so if there are such elements, how many such elements are there? Which frequency will be more than m by k? At most k elements. Good. So my goal will be is that like, let me, so let me fix a hash function of, say, it is from 1 to n, okay, to some constant time k, for example. And what do I want to achieve? I want to achieve that all these heavy guys goes to different buckets. What I want to know, what I want to do, I want to do is that all these guys goes to different buckets with very good probability. But it's a hash function, so it will also be hashing many more items from 1 to. Now, I would ideally like to output. So what I mean, so whenever a new items comes, I say, hey, let's, whatever I'm maintaining a counter for this bucket, let's add to that counter how many times this appears. If something is decremented, I decrease it. But the problem with this object is that this is a overcount, because not only it is going to count with respect to this heavy hitter, it is also going to count with respect to all other elements which are mapped to this. It's going to count all the frequencies. Imagine that this guy maps 1, 3, 5, 7, 9 to this bucket. Then what is this going to count? If all I do that, hey, whenever at first place you are making some changes, please make that change here. So this is change C plus delta 1 blah blah, whatever changes to with respect to this bucket, I have one numbered. So basically it's like a cumulative frequency of all the numbers which are mapped to this bucket. This is what I would like to ideally like to store. So if we choose this C large enough, we can make sure that at least heavy guys are not going into this. But so that's fine, right? So heavy guys are definitely going to go to different buckets, right? So they are not going to collide and make this quantity big. But still, I mean, all these little guys can go and add to these frequencies. So what will we do is that we hope, so there are several ways of dealing with this. Somehow we hope that things are good enough that all these guys are going here and not doing too much of bad things. So this is good. Good quality estimation with very good probability. Like we hope to be lucky. Otherwise we'll try to do something. Or one way will be that somehow try to get estimate of other people here and try to remove from there, right? So if you notice here, what we were returning here at this point of time in Fi hat in Mr. Agrai's algorithm was an underestimate. What we are going to return here is an overestimate, right? Because I'm going to count all the frequencies which is going to be on this hash function and do this. So this is my whole goal, okay? And I just want to be lucky. No, we are not doing 2 passes. I didn't even tell anything. So how are we doing 1 pass, 2 pass? We don't need to do anything. Okay? So let's see what happens if this is all that I do. Okay? So let me write down this algorithm. Let me write down here so that I can use this slide for. Let H1 W, this W we will set appropriately because I don't know what we are hoping to achieve. Okay, be a hash function from n to W. Okay, so this is a hash function. I picked up a hash function. while stream is not empty, what should we do? Suppose I have et, tth time, I and some delta t. What does this mean? Is a current item. It means to ith index make change by delta t, right? So what I do? I do h1, there is a region of writing 1, let's say I have only one, so I h. So what should I do? Where should I go and make changes? Huh? Go to hi. So let's keep a counter, right? Because so in the beginning I have, so let's keep a counter, right? So I have a counter for each of w, right? So this counter will be how many items will be in counter? 1, 2, w, right? C1, C2, CW. It just tells me which place are you mapped to. So this is how should we write it? I don't think this is the right way of writing this. So ith at ith place, but so correct. This is h of I. Like this is the bucket which I am going. Ith item is going to this bucket. What should I write here? C of hi plus delta t. Okay. Let's say and while. Okay. And for I equal to 1 to n, xi tilde, okay, is as I told you. What should be xi tilde? C of hi. This is it. Okay. We will see. I mean, we might need to do more modification, maybe. But so what is C of j? What is counter j storing? Huh? C of? It is sum over, okay, all I such that h of I is equal to j, right, with respect to that I, right, and delta I. I shouldn't be writing delta I because this is one thing, and yeah, this is what it keeps. If you notice, this is what it keeps actually, right? So what is Cj stores at the end? All those indexes for which, so this is what I try to tell you, right? So this is what it is. For some locations are mapped to some place, so I store the sum of these things. This is exactly what it is. So even if you sum them internally, at the end, this is what you're going to get. Okay? Okay. Okay. So as I told you before, we definitely overcount here. We don't undercount here. Right? So whatever I return as xi tilde, I say, hey, this is my estimate. What is my xi tilde? Is my estimate for real xi. So what is the property of xi tilde? Property of xi tilde is definitely is that is greater than equal to xi. This you will agree because of this equation, because what am I outputting? I am just outputting this, right? So you might be counting some more numbers, and this is where I use the fact that throughout my process xi remains greater than equal to 0 at the end. Otherwise, if I don't, I mean, I could have also used like at the end it remains 0, but like greater than equal to 0, but that is not the model which is very well studied. So you assume every time, and so at the end it remains greater than equal to 0. So this is perfectly fine. So you're overestimating. Okay? Okay. So I would like to count how much am I overestimating? Is this xi tilde too much? You get my point? Like what I would like to prove that, oh, this is not too much away from the real estimate with high probability. And that not only I would like to achieve for this particular xi, but this is something which I would like to achieve for each 1 to n that we are able to. But for now, let's just focus on xi. So what is my goal? My goal is to show that probability that xi tilde is greater than or equal to xi plus say epsilon times 1 norm of x. And what is the 1 norm of this? You just sum them in positive, right? So what is 1 norm of x? So if you have x1, x2, okay. So if you have x1 to xn, basically this is what is 1 norm is. Okay. So let's try to compute this probability because that is what will tell us.
It depends on W.
What? Yeah, it will depend. So we'll see how it comes out and then we'll try to fix it rather than fixing it just once in a go. Okay. Okay. So now I'm making a random variable zi. What is zi? Is basically the counter value. What is this? Let's call this the counter value that I has to. Okay. 2. This is my zi. What is the expectation of zi? And what should I write here? What is the probability that xi prime is hashed to the ith, which is same as what is the probability that HL of this and this is same, right? So probability that h of I is equal to h of I prime times xi prime. What is this probability? Huh? So let's assume that this is picked up from not any hash function, but this is picked up from pairwise hash function, pairwise independent hash function. Okay? Huh? What? Is that 1 by w square? It's just 1 by w. Okay? So this is equal to xi plus summation I not equal to I prime xi prime divided by w. Okay? But in our setting all are positive quantity, right? Now it also depends, so now I can take w out common, right? So I can write this as xi plus 1 norm of x divided by w. This I can write it down, right? This is upper bounded by this. Good. So this is my expectation. Lot of things depends on w, which I have not fixed what my w is yet. Okay, but I'm trying to achieve that you are greater than this with probability less than equal to delta. Fine. So now I want to. So this is my expectation of Zi. I want to apply Markov. Probability that Zi is greater than, what is the formula for Markov? It's like expectation, right? What is this? 1 over expectation by A. Okay, fine. This is. So I want, what is the probability that ZL or Zi is more than some, say, beta times this is going to be 1 over beta. Agreed? Okay. Okay, fine. So now here is this quantity. Now to get this, W has to be function of epsilon, right? W has to be function of epsilon. Okay. So let's choose W equal to something which is more than 2 over epsilon. I just choose W which is larger than this. Then what will this imply? Then this quantity will imply that this is less than equal to xi plus epsilon over 2 mod x 1. So now if I wanted to say that this is Zi is greater than equal to epsilon times this, can I say this is less than equal to half? Because is this fine? No? I shouldn't be writing this. Wait. If I write 2 here, then I could have written half. Okay? But my, which is fine, right? Why am I getting
Upper bounded expectation of Z.
J?
Yeah, upper bounded expectation of Z.
Hmm.
You can just separate xi into w minus 1 by w plus xi by w and just make it an equality.
What do you want me to do? How will that help? Will that help?
Which is not, but upper bound won't help it.
Why it will not help? Right? This is an upper bound, right? And I'm saying that what is the probability that, say, this is what I want to show, right? I don't want to say, let's say, what happens? Probability that Zi is greater than equal to xi plus epsilon times, because this is what I'm interested in, right? Right? So what I'm actually interested in is, so if I'm interested in this quantity, if I'm interested in this quantity, right, what is the probability that this quantity is more than this? What is this? This is less than equal to, and if I put 2 here, no, I don't need to put 2 here. What is this quantity? This is half. So look, this is my expectation of Zi. What is an expectation of Zi minus Xi? Is this quantity, right? So just apply there. Okay. But the point is, this is not what we are interested in, right? I was interested in that, look, it should be less than equal to some delta, right? But this can only give me half. So how do I make sure that I can decrease the error probability even further? So imagine that I did not have hash function h, but I had some hash functions. So suppose I had h1, h2, h3, okay, and rather than outputting xi tilde, what should I output here? What do you think should be the best output here? Each of these guys are an overestimate. So if I want to minimize my error, what should I do? I should take minimum of all these guys, right? Each of them are overestimate, right? So if, so rather than having one function, so you take h1, h2, hd, okay? And now you have to be careful, right? Because this is not good enough. So what will you do? For all for all j from 1 to d, what will we do? Hj, and you will put, so now counter should also be changed, right? So maybe you should say counter also has been Cj, right? So now for I equal to, what is this? Min over what? J, Hj, j going from 1 to d. So this quantity will change. So I have taken the minimum over all this. And if you notice here, so the way people think of this as like a, it's like not one hash function, so L cross bra big object, and we have applied this. But now what happens if I apply this and take the minimum? What can I say here? These D hash functions are pairwise independent, okay? So what you are interested in is probability min, right? So for each one of them, you have shown that they are less than equal to half. For each of them, one of them, what is the probability that minimum value of all this is more than this? Minimum over j equal to 1 to d. Now my zi should also change, so it should depend on some j I minus xi, or is greater than equal to epsilon times x, one norm. is less than equal to they are independent hash functions, and you have done independently all these things. So it is here also and it is there also 1 over 2 to the power d, right. So if you give me a delta, I need to show this is less than equal to delta. So now my d becomes a parameter of delta. Okay. So how much d will be? Log 1 over delta. Okay. So my dimension is this. But we have computed all these things just for one xi tilde. We did not compute all these things for each xi. We just fixed one xi tilde, and for that analysis to happen, d has to be this log 1 over f, right. But if I want this to hold with much greater probability, this is not good enough. We need that this guy happens with probability 1 over poly n. And if that to happen 1 over poly n, if I want to make this as 1 over poly n, right, I need to choose here roughly like some log n many hash functions, not just log 1 over delta, but log n many hash functions. Okay. So what you choose now, so now you actually choose d equal to 2 ln n, 2 ln n and by times log 1 over delta, okay, and your w you choose at greater than equal to 2 over epsilon, and now you do all the computations. Okay. So then what happens is the probability that xi tilde is greater than equal to some xi plus epsilon times 1 on x is less than equal to 1 over n square. Now what is the probability that for some xi this bound is not achieved, right. So you apply union bound, right. So there are only n such values. So probability that exists a varying thing is upper bounded by 1 by n. So the probability that you will succeed at each of them is probability at least 1 minus 1 by n. So these are the some computation which you need to do, but things to remember is that what we did is that we had a certain number of hash functions, we bucketed them, okay, we computed each of these quantiles and returned it. Now how much space does it take? How much space does it take? Hmm? So we have log n times log 1 over delta hash functions. Do we need now delta anymore? We don't. If you notice, we don't need it. Don't you think 2 ln n is enough? Do I need log 1 over delta? I mean, look, I am succeeding on all the values with probability at least 1 over 1 minus n. It's a function of n. So if you just increase n large enough for any delta, this should be good enough. Okay. So this is how you will get rid of log 1 over delta. Okay. But how much space does it take? Doesn't matter. How much counters do we have? How much counters do we have? Look, you are maintaining for each of these hi w counters, right. So the total number of space taken is like as much as your counters. So your counters are like d times w, right. So d is upper bounded by 2 ln n, w is upper bounded by roughly say 2 over epsilon. So the total number of counter is like order ln n by epsilon, okay. And how much space each counters take? As many as log m, because so times log n. So that much of space you could take, okay. So we take big O of log n log m by epsilon bits of space. Okay. Okay, we'll do slightly different object tomorrow, which will generalize this in some settings, and then we'll do much detailed computation. Okay, but there's not much happening here, right? All we wanted to compute is that, okay, I have given you an estimate, how far you are away from your estimate, right? So we try to estimate it with respect to the number of like just we took the L0 L1 norm of the whole thing, and we said, hey, you're not too far away from your L1 norm. Okay, so this is what is called count sketch. Okay,
So then delta space for the hash function, right?
yeah. So how much hash function space do you require?
Two log w, two log n. You said two I said.
Yeah. So 2y, so 2 log n times d. Yeah, you also need a space for what is that called? For each of these hash functions. You're right. So we will need how much more space? So, but that's not much, no? How much we need for that? There are log n, okay, and how much big w we need? So some log n bits, right?
W is 2 over epsilon, right?
So ln into
For each hash function, you will have two values, right?
Which is log of that. So it's even better than
log n into log 2 epsilon.
log 2 epsilon.
That's what I said.
And into log 2 epsilon.
Yeah. So which is better than this? Like this is much worse than this number. So you don't care. Okay. So this is what is called count min sketch. So we will do it all together in one go tomorrow, like not trying to build part by part. Okay. But the idea is very simple. The idea is that look, if I take a hash function such that it spreads the big objects into different buckets. So look, if the big objects will collide, then then their sum will become too much. But if the big objects are moved across, then other guys are too small to matter to the frequency of these guys. You get my point? It is too big that even if all other people are mapped to this, I mean they don't matter much. Right? This so to these guys. So why? But these guys are so big in itself that other guys' frequencies are very little compared to these guys, and we can make by choosing minimum over this, we can minimize the what do you call this value of this quantity even much worse. And now next time I'll show you. First, I'll do this again. That sometimes there's a way to also decrease these values from this quantity, and you can get better bounds. So what are better? Here I showed to you that each quantity that I returned is not too large compared to the one norm. I will be able to show you that it is not too large compared to second norm. And second norm is always smaller than the first norm, and in some cases it could be very, very far apart from each other, right? So up until now, I have not decreased anything. My algorithm was, if you just look at an algorithm, right, it is a very simple algorithm. It computes some set of hash functions, keeps some counter, and for each xi tilde as a frequency counter, he say, hey, here, take this number. Now, proof and everything, right? But now we can achieve even better estimate by doing more clever things. And but now we will delete also. What I mean by that, I will not return xi tilde as minimum over all this, but from each quantity, I will have some estimate on how much other people could contribute to this and try to remove this, because all I'm interested in is the frequency of xi, not the sum itself. But this itself was good enough for us. Okay. And one good exercise for you is that, okay, try to think of this as a linear sketch. Why it is a linear sketch? Meaning, can we come up with a matrix A such that whenever a quantity comes, we can multiply by this and we have an update, and at the end we return this, right? I did not do that way. I made my hash functions, I moved. How to think about this? Because that is the most succinct way of thinking about these things. And whenever you have a linear sketch, you allow deletion as well as addition. And that's the only way we know yet. So we were able to manage deletion, right? So there must be some linear sketch which is sitting here, and how do you discover that? Okay, so I think we'll meet tomorrow. So this is called, what is it called? Count min sketch, and we'll do count sketch tomorrow.